Hi everyone, welcome back to the channel. I'm Heinrich and I'm the real nuclear physicist. Today, instead of debunking, we'll be doing something a bit different. We'll be doing an experiment. Now for today's video, I thought let's move away from the debunking side of things and let's go to the science side of things. One thing that flat earthers quite often say is, do an experiment to prove something. So that's exactly what we're going to do today. The experiment in question is, we're going to calculate the rate at which objects fall. I'm going into this experiment without any preconceived notions. So I'm going to see if objects fall at a constant rate, and if they do fall at a constant rate, I will theorize why they fall at this constant rate. Sit back, relax, and enjoy. We'll be taking a couple of objects today, dropping them from a height of 2 meters and filming them at 60 frames a second. I will then use my editing software to count how many frames it takes from the moment I release the object till the moment it hits the floor. I will then use these frames, divide them by 60 to get the time, and then I'll use equations of motion to calculate the acceleration. I will repeat the experiment 5 times with each object. As the scientific method says, it must be repeatable. So I repeat it 5 times, and this also decreases the error that I might get. So first of all, we're going to drop a squash ball. After dropping the squash ball 5 times, we get an average calculated acceleration of about 9,88. So let's see if we drop something else, if we get similar or the same result. So the next object we'll be dropping is a stress ball. Well, for the stress ball we get a similar result at 9,77 meters per second squared. I'll be touching on why we get the difference at the end of the video, but let's move on to the next object, a tin lid. The tin lid, with the larger side facing downwards, we get an average acceleration of 9,7. I'm going to rotate the tin lid and drop it with a smaller side facing downwards, and let's see what we get. Now, with the smaller side facing downwards, we get 9,52 meters per second. And for the last object that I'll be dropping, it's a piece of PVC piping. For the PVC piping, we get an average acceleration of 9,89 meters per second squared. These were all objects with vastly different weights, different volumes and different surface areas. Yet, we get quite a similar result. Now, there are some discrepancies. The thing that I've noticed with the tin lid is that if it falls, it tends to deviate due to air resistance. Now with my calculations, I did not account for air resistance, so that's why there's such a large error in the tin lid values. Yet with the 2 balls and the PVC pipe, all of them weighing different sizes, in fact the PVC piping is completely hollow, we get quite a similar result. Now, the only reason we might not get the exact same result is due to the frame rate at which I filmed. 60 frames per second is not a lot, especially if you go over a distance or a time frame of less than a second. Now, I can repeat the experiment at 120 frames per second and see which results we get, but I'll leave that for a later video. Let's look at why we get these values. Now, there's an acceleration, and the acceleration is downward. Each object has a mass, so that means there must be a force, because Newton's second law of motion says the net force is equal to the product of the mass and the acceleration of the object. What could this force be? You might say buoyant force, but buoyant force is an upward or an up thrust, whereas the acceleration that we experience is downwards. So, what else do we have left that might explain this phenomenon that we just witnessed? Well, there's something that scientists have been calling gravity. And gravity is the force that we experience on Earth, or the force that every object experiences in the universe that has mass. So there's an experiment, it proved something, yet the flat earthers will probably say it doesn't count. So, since they say it doesn't count, let's use the values we got and estimate the mass of the Earth. Using the squash ball with a mass of 24 grams, we can calculate the force it experiences at an acceleration of 9.88 meters per second squared is about 0.2 newtons. Now, using that value and substituting it into Newton's universal law of gravitation equation, we can calculate the mass of the Earth. Now, I'm going to substitute this into a quick online calculator, and the result we get is the following. We can calculate it accurately to about 12%. We're about 12% higher than the Earth's mass, but that's once again due to minor discrepancies in the way we conducted the experiment. So, I now would like flat earthers to conduct a similar experiment and give their idea and show the actual calculations and what you used to prove your ideas. If anybody wants to go and double check my data, you can drop me a comment, ping me, and I'll send you my raw video footage as well as the data that I use to do all my calculations. Now that we've proved that gravity exists, I think we can stop there for today. If you enjoyed this video, remember to like and subscribe. I'm Heinrich, I'm the real nuclear physicist, and I'll see you next time.